Hey, Afzal, can you hear me? Just want to confirm whether you're able to hear me. All right, perfect. So we'll just probably give 2 minutes, Afzal, for just seeing if anyone else is joining. Is that fine with you? Or have you already started the live stream? Giving it a couple of minutes. Okay, I hope everyone is able to also see me. Is everyone able to hear me and see me correctly? And let me also bring up my play. But thanks, Afzal. Thanks for confirming. Let me share my screen. Just one second. Okay, are you also able to see my screen, Afzal? Okay, perfect. So again, welcome everyone. Welcome to yet another session of the Tenseflow user group, third chapter, machine learning study jam that we have been conducting over the last few months. And we have actually done quite a significant amount of algorithms so far. We have covered the KNN algorithm, linear regression, and yesterday we did logistic regression. Today we are now diving a bit deeper into the unsupervised learning space. So far we have covered what is supervised learning, and we covered these two different types of algorithms. One is your the question based and also classification based. So let's now dive more deeper into the unsupervised learning land. So of course, the basic building block of any unsupervised learning algorithm, or the basic differentiation between supervised and unsupervised learning, is on the basis that within supervised learning, whenever we are giving any sort of data, so whatever data that we are actually sending to our ML algorithm, we are attaching the label associated with the data. So if you are giving it images of cats and dogs, we are also providing the label to the machine learning algorithm that this particular image is containing image of a dog and the other image is containing image of cat. So we provide those labels. So we already know what are the different results that are possible. For instance, like if we are providing it three different types of labels, then we know that there are three different classes that are going to be created. Whereas in unsupervised learning, you are providing unlabeled data to the machine learning algorithm. And in that case, what ends up happening is that we get these automated formation, or we get the formation of automated clusters. And these clusters are just on the basis of that, okay, how close are the features that are matching for one set of observations or one set of data? How closely do their features match? Yes, we will also describe to the AI algorithm. We can describe this, that how many number of potential clusters do we actually want to create. That's something that we can command depending on the type of AI algorithm that we are going to be working with. For instance, today we are going to be talking about the k-means algorithm, and there you will see how you can actually define how many set of these automated clusters you actually want to create. So depending on that, we can define, and of course, as you might imagine, that at the beginning, we don't really have any sort of information on what every single data point actually exists, to which particular cluster it exists. So in the initial set of training, there might be a lot of overlap. There might be a lot of error that might be involved when it comes to actually categorizing these particular data points into these automated clusters. There might be a lot of overlap in the beginning, but as you continuously train the algorithm, it will become better, and these clusters that are getting generated automatically will get more well defined and will be more separated out from the other clusters, similar to how any kind of class is created inside of a standard classification algorithm. So that's the gist behind the unsupervised learning algorithms. And let me just go ahead and zoom in a bit more. So what we just covered is essentially unsupervised learning. Let me just zoom in a bit more. So this is something that we covered, which is unsupervised learning, right? And within the unsupervised learning, we have the first category of algorithms, which are clustering algorithms. So clustering, as the word suggests, is the ability to create these clusters based on how the data has been distributed. And you can create these clusters on whether it's like a 2D Cartesian plane, or it could be a line as well. So your data sets will be divided into these different clusters, and then based on that, you'll be able to define, okay, this cluster or this particular data set belongs to this particular cluster, and that we will be able to make predictions from your AI. Data, and then of course we'll also move into how do you actually manage data that may be in two-dimensional, in three-dimensional space, and four-dimensional space, because k-means can be applied to even a linear distribution of data, or even a 2D, 3D, 4D dimensional distribution of data. So you learn for both use cases that if you have either of the two options come up for you as part of your curriculum or when you are implementing this algorithm based on your dataset, how will you be able to actually manage both of it? So that's what we'll basically start off with. So let's take a simple example now. And over here, what I'll do is I will create a line and let me actually create a black line. So let's create a line. And now let's go ahead and add some data to this particular line. So let's say that I have, oh, okay, perfect. And now let's um, have our data over here. So let's say that basically these are the points that we have, and let's draw them out. Okay. So in the first case, let's say that we have this two-dimensional line, right, or one-dimensional line, right? And now basically we have what we have done is we have these three different categories of data. So again, not to basically get confused around what we are basically showing is that let's just imagine that you had some type of data, right, on which you could actually plot a line, and you know basically that you have to create three different clusters. You have to put all of these particular items into three different clusters. So right now, you can like see in this example that all of them have different colors. But in fact, like let's say that we don't know their colors because the colors are actually denoting the clusters, similar to how we had the KNN algorithm where we had all these different points and based on which particular class they belong to, we had different color coding for each and every class. So this is what we want to accomplish. That ultimately there's this line where we have these entire data set out of which every data point belongs to a particular cluster, and a particular cluster can be denoted by a color. So this is what we want to achieve, but of course, in reality, what you would have is essentially just a single line with just your data getting distributed, because right now we don't know which cluster do they belong to, right? So these circles are basically the different points that we want to add to a specific cluster, and we want to essentially detect what kind of cluster would they actually belong to. So, okay, now let's say that these are the set of data points that we want to basically plot on a line, and we'll take the same data and actually add them to the Cartesian plane as well. So the idea is that in this case, we want to work basically with three different clusters. Now, of course, one example could be that through human eye, it could be very simple that, okay, these are four at the same level. So let this one be red, this one be green, but this one be blue. So now let's understand that how does the computer, right, the AI algorithm actually determine what are the different kind of clusters that are going to be formed. So let's understand that. So first thing that we do, similar to what we had in the KNN algorithm, is define a value of k. So k in this or essentially the significance of k over here is that similar to how we had the KNN algorithm, where k basically measured how many number of nearest neighbors do you actually want based on your data that you wish to classify. So your value of k could be 1, could be 50, could be 100, whatever is the value. But of course, there are certain values of k which are going to be giving you good results, that are going to give you more accuracy. So we are leveraging that similar concept of choosing a value of k. And here also the value of k will depend on a lot of factors. And it does not just mean that you pick up any random value k. There, of course, are techniques using which you can find the most optimized value of k. And we will understand that later in this session once we do the Pythonic implementation of the k-means algorithm. So let's say that we have to choose the value of k for now on your own. And for ease of understanding, let's choose the value of k as 3. So the step one, will be pick a value of k. And for now, for this example, let's pick the value of k is equal to 3. So in this way, that essentially what that means is that here, what the understanding of k inside of k means is that we want to find out how many number of clusters do we actually want the algorithm to identify. So if you say that the value of k is 3, it means that we want the algorithm to identify that there should be 3 clusters, right? So that is the main crux. And there are, of course, different other ways in which you can select a more optimized value of k, but that is what we'll actually determine later, how you actually do that. Now, the point is that the second part of the algorithm is that you have to pick 3 completely random data points inside of this entire line. Right. So let's go ahead and do that. We want to essentially just pick up any 3 random points that we can think of. And again, there's no given perspective on how those points should be. That's completely up to you. What those points are, you can choose on your own. So in this case, let's go ahead and pick up 3 different points. So we'll pick up one point over here, which is, let's put this up. So this is point P1, my bad. So this is point P1, right? Then let's go ahead and pick another point, point P2, and point P3. So the step 2 of the algorithm, just randomly pick 3 points in the line. So just pick any 3 points that you want and place them inside of this line. And these 3 points are the 3 initial clusters that we are creating. So the significance of these particular points is that these represent your initial clusters. That doesn't mean that these are the finalized clusters. The next set of algorithm steps will actually help you understand that what we are actually doing with these particular data points, like what is the use of these particular initial clusters. So just randomly pick and imagine that these are going to be your initial clusters. Now, what you have to basically do is that from these initial clusters, you measure the distance between each and every point. So you start with, of course, this particular point, which is, and I'll just mark this over here. So you basically start with this first point and basically measure the distance between the first point from all these 3 initial clusters and assign the color to that particular point based on whatever is the closest cluster near to it, right? And do the same thing for all of the other points. So what we are, and I'll basically do it for one point over here. So what you want to do is that you take this particular point, let's name this particular point as point A. So this is point A. And now what you want to do is you want to basically, you want to so we will assign the value of red to this particular point. Similarly, if we do it for the second point, it is nearest to red, right? Similarly, this one, it is nearest to red. This one also nearest to red. Then if you look at point P2, all these points are perhaps closer to point green, to the P2, right? Then I guess all of these 6 are nearest to the point P3. So essentially, again, what we're doing is we are repeating it for all the other points, and we just find that you calculate the distance of that particular point from all the three different clusters, and whichever is the nearest, you just assign the color of that particular cluster, or that essentially means that you're assigning that particular cluster to that particular point. And this way, what we are doing is that we are so if I just want to basically understand this over here through writing the step. So step 3 is calculate the distance of each point from the three. So calculate the distance of each point from the three um, clusters and measure the shortest distance and assign that particular value of the cluster to the given point, right? So this is our third step. So this is going to be our third step where we took the measurement and we calculated the distance from all the different clusters, and the shortest distance was given the cluster, right? So we assigned the cluster based on the shortest distance. Now, this is the first iteration, and there will be multiple iterations. So once we have basically assigned the point to the nearest cluster, what we do is that this way, like as we have done it for all the different points, and we have measured all the different other points as well. Now, basically, what we have that now, since we have all of the different values and we have assigned them, what we'll basically do is that we'll calculate the mean of each and every cluster, right? We'll calculate the mean value of each and every cluster. So for the red value, for the green cluster, and for the blue cluster. So in this case, and the mean is basically based on that for all the different points that are belonging to a certain cluster, we calculate the mean of all of their values, because we know that, okay, like this is the red. So of course, they'll have a mean, right? Similarly, like all of the red ones will have a mean. So we'll basically identify where the mean actually lies. And it's not necessary that the mean will actually lie on the point of the initial cluster, but we will just calculate the mean. So for instance, like if the red mean, I'll just remove, this particular point. So we are now removing. Oh, so let's just go ahead and remove the spot. I think let's, or I can just go ahead and, so for example, now if you want to just calculate the mean of all these values, so it would essentially be, let me actually remove this one. This, no, it's not. You already know that this is point P2, P3, and P1. So the largest circles denote that. Now, what, of course, according to the algorithm, we will calculate the mean values. So let's say that these are the mean values that we have calculated. So these are the mean values. So these 3 points denote the mean, right? The mean value. So our step 4 is to calculate the mean of each cluster, right? So we calculate basically the mean of each cluster based on how the points were actually distributed. And based on this now, what would essentially happen is that we will now repeat the process that we did earlier. That we will now calculate the distance of each and every initial point that we picked up from the mean. So earlier it was from that initial point that we declared that that is our cluster. But now instead what we're doing is that now having calculated this mean, we will again calculate the distance of the particular of each and every point in our dataset from these particular mean values. So if I just perhaps draw this out again, just for simplicity. So let's just draw these over here. So blue. Then think for the red one, we should be over here. We had these 2 points. Right? Then green was over here. Yeah. So these are the points. So again, calculate the distance. So in this case, it would be from here. So you are calculating all of these different points. And again, you find that what is that nearest value. So in this case, this one would be red. This one would also be red. This one will also be red. This one will also be red. These two will be green. And this one might or might not be green. Like, I think it's closer to the green. So let's just make it green for now. And then we make this one blue. This will be blue. This will be blue. So we repeat the same steps that we did earlier to look at every single point that we have to put into a cluster. We calculate the distance from each and every different mean values this time, and then we calculate. And now, after having repeated this for all the different points, we will again color them based on this. Now, the point over here is that, and the goal over here is that why we are doing this is once we see that after having changed our mean values, or essentially because what we did was after we calculated the mean value, the centroid or the center of that particular cluster actually changed itself. And in this case, what we happened to see was that we had a new value come up as our, like we had a change in the colors of these particular clusters, right? So that means that we had a change in the values to which particular cluster that each and every particular point belonged to. So there was a change. But let's say if there wouldn't have been the change, that would have basically been the end for us, in at least in this example. But of course, as you continue to iterate over it, you'll see that as you change the values of these mean, as you change the values of the means, right? Of course, as you're calculating the mean again and again, it will change the location of this particular point that you see, right? So this particular point will keep on shifting. And once you reach to a state where these are actually, where the points that have been classified, they remain as it is. Like based on, for example, in this case, now we had 4 in the red one, 3 in the green one, and 5 in the blue one. If in the next iteration, I will again calculate the means, I'll have a 3 new set of mean values, and I will again calculate which particular cluster should each of these particular points belong to. If it remains the same as the previous iteration, then that means that we have reached to an end. But that does not necessarily mean that we are actually having the accurate result. Because initially, what I actually wanted was this thing. Our ideal case would have been something like this. But what you see is that after having taken this as an example, right, where we just picked up 3 random places, it gave us the result as this, where 4 are from red, 3 are from green, and 5 are from blue. So as you can see that this particular cycle was not actually correct. So what that would mean is that it does not mean that the initial points that you basically selected, it will always give you the correct result. It actually did not that great as compared to the real values. So we can always adjust the quality of the clustering by basically adding up the variation that we have based on each and every cluster. So basically, similar to how we calculate the variation in the linear regression algorithm, where, if you remember, we had the linear regression line and all of the observations are there. So your total variation is basically calculating the sum total of the error, which is basically based on the observed values and the actual values. If there is a big difference between them, then you can say that, when you sum up all the errors, then you get your total error. And our entire goal is to minimize this variance as much as possible, because more the number of variants, that means more is the inaccuracy. So we can always assess the quality of a clustering by adding up the variation of each and every cluster. So in this case, for example, if we want to calculate the total variance, right? So if you were to describe the total variance in this example, right? How much would that be? So you basically calculate, okay, for red, it is it is basically this. So red, it is this. This is the entire variance, right? And for green, it is this is the variance from the mean value. So you always calculate the variance from the mean value. So this all denotes the total variance. So if you now add all of these differences between the mean value and your data points, because again, the difference between the variance means that if you denote them on a plane like this basically tells you how close is the data actually distributed to the mean value, right? So the idea is that within the k-means clustering, you cannot actually see what might be the best clustering. The only option is to basically keep track of the clusters, calculate the total variance, and then shift your initial points, which you consider as your initial clusters, and keep on calculating the variance for each of those particular points. And this way, what you'll identify, or what you can try to find out is what is the total variance that you get based on the initial set of clusters that you basically select. So you identify all the different points, you change the initial set of clusters, and again calculate the means and recluster based on the new means. And you repeat till there is no other change, and then you calculate the total variance, and then repeat it and do it over each and every time by selecting new. And then you see that, okay, based on multiple attempts, the attempt that gives you the least amount of variance will actually be the most accurate value. So this is essentially what you do. Now, of course, the question arises that, okay, how do we figure out the value of k, right? So this is in a nutshell what the k-mean algorithm means. So let's also understand that how do we actually select the value of k? Like, what do we have to do to find out the value of k? Now, of course, you can select it as we covered earlier, that you can select whatever value of k, right? For example, if you would have had this kind of data, right? So if you would have had this kind of data where there are three different, like there are three distinct kind of data points, then you'll basically start with k equal to 3, right? Of course, it makes sense to have k equal to 3. But if I would have chosen k equal to 1, right, what would have happened? It wouldn't have necessarily given us very good results, because k equal to 1 would is basically the worst case scenario, because you can quantify its variance by seeing like how much amount of variance there will be, right? Now, if you would have taken k equal to 2 instead, so what would have happened is that, now let's say that there would have been 2. So in this case, like the total variance that you would have got from k equal to 2 would have been actually been lesser as compared to k equal to 1. But if you would have chosen k equal to, can see that as we add more number of values of k, the total variance that we actually get is slightly lesser. In fact, like if you take the value of k is equal to 4, right, you'll have 4 different points that you basically calculate. So the total variance of within each cluster will actually be less than when you have k equal to 3. So that is like the idea is that each and every time you add a new cluster, the total variance within each cluster becomes smaller, and where there is like point where now we don't see any much difference in the variance, that is the point that we are essentially coming to a conclusion. And essentially there is this graph that we can create. So basically it looks something like this, where the idea is that you reach to a certain point which we call as the elbow point, right? So it is called as the elbow point. And this elbow point, essentially what it means is that there's a huge reduction in the variance that actually goes after you reach to a certain value of k, after which the variance does not actually go down as quickly. So usually the point where you reach to that elbow value is where you can safely say that, okay, this is perhaps my most optimized value of k, and this is the one that I should proceed with, right? That is like, this is the most or this is also called as an elbow plot, right? Because you essentially pick up the value of k by choosing the value of the elbow point, because from there, like, even if you pick up a higher value of k, the amount of difference that you'll get is not going to be that much, and choosing a higher value of k will in fact like increase the amount of compute that you'll basically have in your data. So, of course, this is an example where we covered how do you actually imagine the k-mean algorithm inside of, a line. But now let's also imagine it in terms of how would it actually happen inside a Cartesian plane. So imagine that this is again all of the different points that we have, right? So all of our data, again, what we'll do is we'll pick up three initial points, and this time, what we'll do is that we'll calculate the Euclidean distance between each and every point. So we'll calculate the Euclidean distance from each and every point, like we did in the KNN algorithm. And what we'll do is that we'll basically assign the point that is nearest to that particular cluster. And then, so first, let's go ahead and do that after calculating that. So let's say that these are the points, right? So let's assign them the colors based on what is the nearest point. Okay. So what we have done is we have taken three initial set of points that we just thought of as our centroids, and then we went ahead and calculated the Euclidean distance of the points, right? So you can calculate the Euclidean distance between any two points, and we calculate the Euclidean distance of each and every point from all the different initial clusters that we have set. And what is the smallest? We just assign that particular cluster to that particular point, right? And now what we do is that we'll again calculate the center of each and every cluster. So in this case, we are basically calculating the centroid, right? So in this case, like let's say the new centroid is marked over here, and for this one, it will be over here, and for the green one, let's say it's over here. And we will basically again repeat that same process that we had in the line. We'll again calculate the Euclidean distance from all the different points. And we'll keep on doing it a few more times until we see that, okay, that between two separate iterations, we didn't have any difference in the change in the values associated with that particular cluster, right? Because initially there will be a lot of changes when you are changing, because you're just assigning three random points, and you're continuously like just changing, right? So this is what we are going to be studying. So even if like you have, let's say, a heat map, or so for example, if you're having a two-dimensional data, so that will have the y and the x coordinate, your Euclidean distance formula would be x square plus y square. But now if you have, let's say, a z-axis, you can just add plus z square. If you have a fourth dimensional axis, you can add plus a square. So and so forth, like you can continuously change the value. So this is in a nutshell what we have with respect to how, just to understand like what k and k-means algorithms mean under scenes. So it took us a bit more time to explain this, because like there is this it's definitely different as compared to your typical algorithms that we usually study with, like the KNN algorithm, the linear regression, where you're not necessarily changing the means. Like the mean values are set for you, because you know what are those classes that are going to be created, and you're not specifically changing those. But in this case, you are essentially changing the cluster and where the cluster is actually located based on how the data is actually getting interacted, and how what's the closeness in the data, right? So that's one of the major differences between any unsupervised learning algorithm and a supervised learning algorithm. So let's now look into the implementation phase of this particular algorithm. So I'll bring up my Google Colab. I'll create a new notebook. All right, let's connect this. I'll keep the name as k-means. Okay. So let's look at the k-means algorithm now. So first, what we need is basically to define what should be the number of clusters. So calculate the total number of clusters, which will be defined by the value k. Next thing in line, we want to calculate how many number of centroids actually need to be created. So since we are dealing with an XY Cartesian plane, initially we said that we are just taking 3 random points on the line. Since we are now dealing with a Cartesian plane, we'll say that we'll select an initial list of these randomized centroids, and we'll have as many number of centroids as we need the clusters. So in this case, we'll basically define k number of initial centroids. Next thing that we'll do is that every point, assign every point to the nearest centroid using Euclidean distance. So in order to identify what is the nearest centroid, we use the Euclidean distance. The next step would be, as we covered, that you recalculate the centroid based on the mean of all the data points in that particular cluster. So you recalculate the centroid of the cluster by calculating mean of all the values belonging to that cluster, right? And then what we'll do is that we'll essentially repeat the steps 3 and 4. So assigning the point to the nearest centroid and then calculating or recalculating the centroid of the cluster. We'll repeat 3 and 4 until we reach the state of convergence. So what does that mean? That means that centroids are no longer changing significantly. So, or for a specified number of iterations, that you saw that for iteration 4 and 5, the centroid positions actually did not change. That is a good observation to say that we have reached to the conclusion of that particular value of those initial centroids that you actually set. So let's dive deeper into the code of how this is actually used. And we'll use the sklearn.datasets library to grab like a random dataset. And we'll also create our necessary class for the means. So let's go ahead and define. And let's just import over here numpy plus np and import, we'll import sklearn.datasets and we'll import make block. So make block specifically because this is going to be a clustering algorithm. So the make blobs is a good dataset for being able to visualize different clusters that you create. So it's good, and I think it's make blobs. Okay. Perfect. Now let's go ahead and create a new class, which will call k-means. Within this, we will first just initialize our init. This what will pass are primarily how many number of clusters. So we'll define that particular value as n clusters, which is nothing but it's the k value. And how many number of iterations of this entire cycle do we actually want? So the iterations over here is that, okay, you can essentially do this iteration of recalculating the centroid, assigning it again, and then assigning every point to the nearest centroid. So that particular step 3 and 4, you can continuously do it till infinity. But of course, you don't want to do it till infinity. You want to do it till a maximum number of iterations. So you have defined a value over here, which is the maximum iterations. That beyond this, you should not have more number of these cycles of repeating this particular value. So, and we'll just define the self n clusters with s cluster, and then just to initialize this particular value. Now we'll define a function fit, which will of course self, and we'll have basically list of values in x. Now for what we'll do is that we'll say that So over here, what we first have to do is that within our fitting, what we have to do is we have to the first thing that we have to do is we have to initialize our centroids. So as part of the first step, that you pick how many number of clusters you actually want, and then you define what are a set of k initial centroids. So let's go ahead and first define our set of k centroids. In this case, we can say self dot centroids is equal to. So we are going to be having both, the x and the y coordinate. So in this case, let's actually just use this. So what essentially this is doing over here is that we are using, of course, we are using NumPy, and we are basically getting a random choice of x dot shape. So basically, the x dot shape is your initial all of the list of values, and we are picking one of those, and then of course we have a total number of clusters being um, based on how many number of centroids we actually want. So we are defining that over here, which is the total number of points that we actually want are 3. So this will allow us to select or choose our initial set of centroid values, right? So this should be good enough to give us that initial values. Now what we'll do is that we will take these and have a loop in order to basically give each and every so to give each and every data point and identify what is the nearest cluster to it, right? So, oh sorry, nearest cluster to it. So we have to assign every point to the nearest centroid. So that is what we'll do in the next step. So let's run a loop. We'll say for I in range, and this will run till the total like till the maximum iterations that we have, right? So maximum iterations. And in this, what we're doing is that we'll basically assign each data point to the nearest centroid, right? This is what we want to accomplish. So in this case, what we'll do is that we will, let's say, have a variable called as labels. So labels will help us to identify what is the nearest label, right? Based on the Euclidean distance that we calculate from all the different centroids for each and every point, which is the nearest one. So we'll assign that particular label. So in this case, let's just for now, we'll have a separate function that we define for doing this, which we can call as assign labels. So let's call it assign labels. And here we will pass x. And what we'll do is that now we have to basically update the centroid. So once we have actually assigned each and every point, we have to recalculate the centroid of the cluster by calculating the means of all the values belonging to that particular cluster. So the new centroid will be the new mean that we have just found out. So let's define our new centroid. And this new centroid will be equal to self. And here we'll again later on define another function which we can call as update centroid, where we are passing our x and the labels based on the new data values that we actually have. And we'll have another condition where we actually check for convergence. So this is important to see, okay, in our given 100 iterations, we don't need to necessarily run all of the 100 iterations. So let's say that by the 50th iteration, we have found that for the last 10 iterations, our values of the centroids are pretty much the same. So that is a good measure to give us that whether we have actually reached to the desired state of identifying our final set of centroids, which are now going to be fixed. So that means that gives us the final set of clusters, and there are no other changes happening. So the data points are still assigned to that same cluster that they have been assigned for a number of iterations now. So you check for the convergence, and again, it's fairly simple to say that if in P dot all, if all of the centroid values are equal to the new centroid values, right, then we can say that just break out of, so this can be removed. I think, yeah. So we can just break out of it. And then what we'll do is that finally we will just assign the new centroids to the old, like we'll assign the current set of values of the centroids with the new ones, which we have just essentially calculated. So all of this is essentially what we are having with respect to our for loop, in which we are iterating over each and every value till the time either we finish, or I think this is from sklearn import. So this should be fine. So this will allow us to calculate what is that value of the k, right? That will allow us to get that final list where now we are not seeing any significant changes happening in our data set. So now let's also define both of these functions that we created over here. So we'll have def assign labels. So here, better now? Okay. So I want to see that this is aligned correctly. Let's see why is this unintended amount is not what its previous intent. Okay. Not sure. Perfect. So now we will go ahead and assign our labels. So in this case, for assigning, we'll just simply say that we have to, of course, compute the distance, right, from each point to the centroids. So that is what we have to calculate. So we'll say that distances, and here, of course, in the K-NN algorithm, we also use the Manhattan distance. We used different type of distances. Here we are going to be calculating what is going to be the Euclidean distance from all the different points, and we will do it for each and every particular centroid. So we'll calculate that. So we'll use np dot, and again here what we are doing is that we are using the linear algorithm, right, to normalize this entire data. And in this case, what essentially this means is just to kind of also understand, like if you were to understand, like what this particular line means, let's see. So essentially what we're doing is that we are calculating the Euclidean distance of all the points from the self or centroids, where we are basically adding the new axis, which allows us to broadcast when subtracting from our centroid, right? And this essentially does it for all the different, so because of course, right, we don't just have one loop. We are calculating the Euclidean distance of each and every point from all the centroids and calculating which is the smallest distance. So this together will be able to give us that particular value. And then what we'll do is that we can remove this particular line. Instead, what we'll do is that we will essentially assign the label based on the nearest centroid. So let's go ahead and do that. So here it would be the minimum value where we have distances and x equal to 0. And now what we'll do is we have basically gone ahead and returned this. So instead, like what we can do is we can simply return labels. Okay. Now let's also create a function for updating the centroid. So here we are passing our self Excel labels. So this is once we have assigned the new values of or we have assigned the labels each and every point, we have to basically compute the new centroid by taking the means of all the points in the cluster, right? So let's go ahead and now calculate the new centroid. So this would be new centroids will be equal to np.array. And here what we're essentially doing is that again what we're doing is that we are basically taking each and every label, right, one at a time, and we are calculating their mean based on the axis 0, and we are doing it for our each and every cluster that we actually have, right? So ideally this should give us the result. Just close this. Okay. So essentially this is what we are basically getting, where we are running it for this entire range, and then what we can do is we can return the new centroids. So this will return the set of centroids that we have, right, to our data. Now let's go ahead and generate let's generate synthetic data. for sklearn, using sklearn dot make blobs. In this case, we'll use the make blobs function. With samples, we can take 300, and perhaps centers, of course, we'll have 3. Random state will select as 42. So this should give us the value. And then we will go ahead and create a k-means instance by picking up an initial value of k over here. So in this case, let's pick up the value of k as 3. In this case, we are defining our k-means with the n number of clusters as 3, and then what next thing that we have to do is we have to basically we have to fit the model on this particular data, right? Because we have just created our data. The next thing that we have to do is that we have to basically get the cluster assignments from each and every data point. So we have to get the cluster assignments from each and every data point that we have in the set of clusters. So let's go ahead and do that. So that would be the labels, and we'll call assign labels, and we will now so once you have gotten these labels, right, then what we'll do is we can print a couple of values. One is let's say the cluster assignments or the labels. And here you can pass the labels, and then you can also print another value, which would be the final centroids. And here you'll pass the k-means dot centroids. These are the list of final centroids which you will find after you have run this entire algorithm. So let's go ahead and see that how this will basically work. So let's run this, and let's also run this. Boolean index did not match next array dimension 0. The corresponding Boolean dimension is 3. Okay, let's see. New centroids. So might be getting an error over here. Let's just try to ask Gemini quickly. I just have to verify what. Okay, let's see. So it says that the Boolean index did not match the index string along dimension 0. Okay, that actually makes sense. So see, like basically what you're doing over here is that the total number of samples of the data that we want to use. We'll have the samples defined over here, and then the random state over here. Then we pass the number of clusters. In this error, we are getting at line number 56, and we're also getting at line number 40. This is going to be the new cluster. So the new centroids that we're calculating. This is where we are getting index. Boolean index does not match the indexed array along dimension 0, but corresponding dimension is 0. Okay, makes sense. So basically what we are doing over here is we are calculating, of course, the updated centroids. So we are calculating np.array, and here we have passed labels equal to I, and then we are calculating the mean along that's 0, and we are running it for the range that's there in clusters. So I believe this should be fine. Let's compare. Just give me 1 second, folks. Let's just try to understand why this might be throwing an error. Because normally, like what would have happened is that they would have given us all of the cluster assignments, and then let's see. Let's see if you're able to fix this particular issue based on our value. Labels that we're defining is basically a 1D array, and we are trying to compare it directly to the list comprehension. So, okay, so what does it allow? What does it tell? Is so this is a change. Okay. So the Boolean index did not match 300. This is happening when you are comparing is being calculated 0, 1, and 2, and you're trying to compare it directly with I, which is the list comprehension, which makes sense. Let's just go ahead and copy this and paste it over here. Go ahead and make this. Okay. Still did not necessarily fix. Let's see. Still gives us the same error, I guess. Yeah. Mm. So in this case, like what is happening is that when we are actually calculating, what I can also understand from this error is that when we are essentially using the update centroid method, and we are calculating those new set of centroids, here essentially when we are comparing the label equal to I, that is basically the Boolean mask, right? That means the values that are 0, 1, and 2, it does not actually match with the first dimension of that entire array, which is all of the list of values that you actually have. So what we are doing is that we are handling empty. Okay, that actually makes sense. So let's go ahead and try to use this particular one instead and remove. Hopefully, this should. Okay, perfect. So that gives us the list of values. And as you can see that it also gives us the list of the final set of centroids. So in this code, what we have done is we have created the k-means class, fit it to our sample data set, obtained the cluster assignments. And this basically implementation will now help you understand the core steps that are involved with the k-means algorithm, which is initializing our initial centroids, assigning the labels, and updating the centroids iteratively. Now, of course, one main point to also consider is that now what to actually do if we were to visualize these particular events, right? What to essentially do if we were to visualize all of these particular data points that we just saw, right? Because ultimately, what is going to make a sense is that how do we actually also then visualize them, right? So now we will also go ahead and calculate or work with a project to understand that how you can actually implement the k-means algorithm. This was a sample dataset that we leveraged, but let's actually build a project now. So what we'll go ahead and do is that we will just take a sample dataset where again the goal is that you can understand that how before k-means you have all of the other, like all the unlabeled data, and then after the k-mean algorithm you have basically labeled your entire dataset, right? Because that is what is going to be there. So we'll now basically work on building a project, and from there we will go ahead and discuss this. So what we're going to be doing is that we are going to be taking an entire set of data. So here we'll basically use the dataset over here. So this is the dataset that we are going to be using, which is the UN News World Report of the college data. So basically, what we are going to be using over here is that we have like if you look at the data, you have all of these different values, which are whether whether the data is actually private or not. So in this case, whether it is a private university or public university, then we have apps, which is the total number of applications received. Acceptance is basically how many number of applications are actually accepted, how many number of students, new students are actually in, they have been enrolled. Then what are the top 10 percentile of the highest class that you have? What is the top 25 percentile of the class? What is the total number of full-time undergrad students? What is the total number of full-time, part-time undergrad students? And then finally, how many total number of outstation students? And you actually have more number of columns. So you can, of course, you can maximize the view and see more because it's not showing all of the columns. You also have like whether there is a boarding room, what is the room of the board, and then what is the estimated book cost. what is the personal spending that you'll have to do, what is the faculty with the PhD. Terminal is basically how much you are estimated spending. SF ratio is basically like the student faculty ratio, percentage of the alumni, right? And then finally, how much expenditure would be there per student, right? And what is the graduation rate that is there in this particular university. So all of these particular data points are going to be used, and I'll include the link of this over here. So we are going to be using this particular Kaggle dataset. This is the one that we'll use for the building of the project. So let's close all of these because we don't need them. And now, again, the point over here is that let's go ahead and also insert all of the important libraries. So import NumPy as NP, import pandas as PD, import matplotlib as PLT, and then import Seaborn as SNS. So let's now proceed with actually getting the input dataset. So what we'll do is let's download this dataset and import it over here. And now we'll just say df equal to pd.read_csv college.csv. And just go ahead and run this to identify. And you can see that we have received our entire data. So all of the data that we have received that now. Let's proceed further. So this is our entire data. Now we can also just quickly have a look at the info. So df.info, and this gives us all of the data, including how many number of values that are there. So you have a total of 777 results that are going to be there. We can also go ahead and describe our data set totally what you want. Now we can also go ahead and actually visualize how our data set actually looks like. So if you want to just see that how the data is going to be visualized on, like, let's say a plot, because of course then we'll actually create the clusters. So let's use sns.setStyle. Here, let's create a style as, like, let's say a wide grid. And then we'll have sns.implode. So or actually, Helen, let's plot this. So what we want is basically the the total number of boarding versus the graduation rate. Let's identify that for, like, let's say the private universities. So what we are doing over here is we want to basically create a scatter plot of the graduation rate versus the room boarding and find out where are the points which are colored by the private column. So let's go ahead and run this once. Data equal to df. Let's see. Got multiple values of data. Okay, let's just quickly take a look. So size should be 6, aspect is 1, is false, and data equal to df grad.grade. See, why were we getting this? Just print this out. Okay, let's perhaps rename. We cannot rename the plot. Let's see. So this. Okay, I mean, for now, let's ignore that because that's just, we are just basically plotting it. We could try out another plot as well. We can say just use the same here, but instead what we'll do is that now we'll say, okay, how many are outstation? So outstate versus f dot, like, let's say how many undergrad students are there. So basically creating a scatter of plot between the undergrad versus outstation student. So undergrad, right? So this should be undergrad, and then data equal to df use private. So we might see the same error. For now, I think we can, but this would have basically given you like how that kind of looks like. But anyways, let's proceed now with, seeing, okay, we would just want to identify that how many of these values are actually from a private school where the graduation rate is actually higher than 100%. And we want to identify how many of such schools that are there. Let's do a DF of DF where basically the grad rate is greater than 100. So we'll get the result over here, which is basically the California College, where the graduation rate is greater than 100. And then what we'll do is that basically we'll set the graduation rate to be 100 because of course graduation cannot be more than 100. So let's set the graduation rate for this particular California College to be 100 because it doesn't make sense to be more than 100, right? Because it cannot be more than 100. So that's a value that will actually need to be improved. And now let's go ahead and create our actual clusters. So we'll use basically the from sklearn dot cluster. We'll basically import k-means, and then we'll say k-means, and we'll just initialize the value, and we'll create, let's say, two clusters because we want to find it between the private and the public school. That is why we will basically fit the model except for the private label. So let's use k-means dot fit, and in this we'll pass df dot basically drop private, and here we provide access equal to 1. Okay. Let's not convert string to float. So we'll also have to what we have to do is that we'll have to uh, essentially assign each of these particular values to like private value, because of course right now, of course, we cannot directly implement our the algorithm directly on top of like string value. So you'll also have to convert your entire column. So of course you can always just take the column and then either convert it via one-hot encoding, or you can leverage some other means for taking each and every value, because it's not just like the Albaline Christian University, that's the first value that you're getting, but of course all the values that are there in that particular cell will actually have to be uh, dropped. And I think we had actually written that, but let's just use this over here instead. Yeah. So I think basically the thing is that we are converting it into a numeric value. That's what we are essentially trying to do. So let's see that we're able to get this fixed quickly. So you're basically converting all of the non-numeric columns into numeric. Just quickly go ahead and copy this. And private is already run. So like let's just create, we'll just run the data frame again so that we have it running. And yeah, let's just quickly fix all this. Perfect. So our k-means runs successfully. Now let's go ahead, and after we have basically fit the model, let's essentially evaluate the performance, right? So what we'll do is we'll first find out the cluster centers that we have got. So k dot cluster centers. these are the set of cluster centers that we have. And of course, I mean, there is no perfect way of basically evaluating the clusters if you don't actually have the labels. However, basically for exercise, let's say that if we do have the labels, we can basically take advantage of that to evaluate our clusters. But in real world, it might not necessarily mean that we have the clusters. So let's say that we have a converter where we pass the cluster inside of this, and then we just say that if cluster equal to yes, right, then we'll basically go ahead and we'll return one. So we are saying that df converter so we'll say if cluster is equal to yes, then we'll simply just return one, else we'll return zero. Right, so let's go ahead and run this. And now what we'll do is that we'll say that df cluster is actually equal to df private, and we'll apply the converter over there. All right. And now we'll say we'll just find out df.head. Let's see what do we get. So what we see over here is that, and we can also always like create the confusion matrix, right? So for that, we can just simply always go ahead and create confusion matrix to find out, what is the set of values. So in this case, what you see is that we are looking at the confusion matrix and the classification report to see how well the k-mean algorithms work without being given any labels initially. So you can see the number of false positives and false negatives, the true positive and the true negatives. So all those have been generated over here. So again, the code for all this will be provided. So this was an example of how you can look. Perhaps I'll just look into why why we're not able to plot this over here in later. But yeah, I hope this gives you an idea of how we implemented it. Thank you, everyone. So we can conclude the session.